Welcome one, welcome all. How are you guys today? I'm glad to hear it. I hope you guys are well. I hope this does nothing to change that. It is Tuesday, our second happiest day of the week. There was a test being proctored in the room where we normally do our recording from, and no students showed up this week for our problem session. So I decided to do our problem session from my office. Hopefully the video quality isn't too terrible. Let me know if this is a problem, and I'll make sure that I don't do this again if it is a problem. So let me swap cameras so that we can see what we're doing. Since we just started our tour of optics, I thought that I would start by giving us a little bit of background. So I'm only going to do a few problems in our problem session for today, so I don't get too far ahead of our lecture. But I did want to give you this relativistic Doppler effect for light. So this is specifically for a light wave, and this is the statement where the source and observer are approaching one another. And so in this case, the observed frequency is the frequency is measured by the emitter multiplied by the square root of 1 plus u over c divided by 1 minus u over c and quantity, where u is the relative velocity, or in this case, the magnitude, the speed of the relative velocity between the source of the light wave and the observer of the light wave. And I'll note that, remember, this is for the case of the source and observer approaching one another. If the source and observer are moving apart from one another, then just sub out u for minus u. So everywhere you see a u, turn it into a minus u. The other thing that you could note is if we multiplied top and bottom by the square root of 1 plus u over c, then the numerator becomes 1 plus u over c, and the denominator becomes 1 minus u squared c squared under the square root. If instead we multiplied top and bottom by the square root of 1 minus u over c, then the denominator becomes 1 minus u over c, and the top becomes the square root of 1 minus u squared over c squared. So hopefully this algebra is not terrible for you. So I'll again remind us, this is the case of the source and observer approaching one another, and if you want to swap out the case where they're moving away from each other, the u's all become minus u's. This is only true if they are moving apart or moving apart or moving towards one another. In other words, not only that, but also the direction of the propagation of light is parallel to the direction of the relative motion u. In the case where they're moving apart from each other, but the direction of propagation of light isn't parallel to the direction of the relative motion. In other words, the direction of the propagation of light differs from the direction of relative motion by some angle theta. Then what we have is the observed frequency is the emitted frequency multiplied by the square root of 1 minus u squared over c squared divided by 1 minus u over c times cosine of theta, where the direction of propagation is theta. So notice that it looks very similar to this case, right? The only thing that we're really doing is we're adding this 1 over cosine theta. Yay? So let's try a couple examples using these relationships. So these formulae. And then we'll try one for the law of reflection that we talked about in lecture yesterday. So first example, let's say that from experiments in our lab, we note that there's a spectral line associated with hydrogen emission that in our lab, we note shows up at a wavelength of 121.6 nanometers. We then turn to look at a distant quasar quasi-stellar object, moving away from Earth with speed u. When we observe the same hydrogen emission line from this quasar, what we find is that we see a wavelength of that emission line at 460.9 nanometers instead of 121.6 nanometers. If we assume that the quasar is moving radially away from us, let's then use that information to determine the magnitude of this relative velocity u. So here we can turn back to our equation here, except that note that because the quasar is moving away from us, we need to sub the u's for minus u's. And so we can say that F is equal to F naught times 1 minus U over C divided by 1 minus U squared over C squared. Yay? Note that all we did here is we subbed U for minus U, so 1 minus U over C, 1 plus U over C becomes 1 minus U over C, 1 minus U squared over C squared. Well, if I plug in minus U for U, minus U squared is still U squared. And so 1 minus U squared over C squared still looks like 1 minus U squared over C squared. So from here, we can remind ourselves that C is equal to F lambda. And so this equation just looks like, if I want to solve for F, C over lambda is equal to C over lambda naught times 1 minus U over C over 1 minus U squared over C squared. We can manipulate this. Notice C on both sides, I can just cancel that. And we could get then that lambda looks like lambda naught times 1 plus U over C over 1 minus U over C, right? So in that case, we could divide across, get lambda over lambda naught is 1 plus U over C over 1 minus U over C, square both sides, and then solve for U over C. If we do this, we get that U over C is equal to modulo little algebra, lambda over lambda naught squared minus 1 over lambda over lambda naught squared plus 1. Now, lambda is 460.9, lambda naught is 121.6, both nanometer. And so lambda over lambda naught is about 3.79. Plugging that in we get that U over C is about 0.87. In other words, the quasar is moving away from us at about 87% the speed of light. Remember, the speed of light is 3 times 10 to the 8 meters per second, so 0.87 times 3 times 10 to the 8 meters per second. Did that work for you guys? Questions, comments, concerns? So this is about 2.61 times 10 to the 8 meters per second. Hopefully that worked. Let's try another one. So this time we are given a very badly drawn satellite that is orbiting in a circular path over Earth's equator. There is a ship sitting still in the ocean, also on the equator. The satellite is broadcasting radio waves of frequency 122.450 megahertz. If the satellite is 153 kilometers above the surface of the Earth, if the ship wants to tune into the frequency broadcast by the satellite, let's examine where they should tune their radio to in 3 cases. One, when the satellite is directly overhead, so right here. One, when the satellite is the longitude 10 degrees west of the ship, and one where the satellite is at a longitude 10 degrees east of the ship. So the satellite is passing from west to east. So when phi is 10 degrees to the west, and then part C when the satellite is at an angle phi 10 degrees to the east of the ship. So we need to tackle this in a couple of parts. And so the first I'll remind us is that our sum of the forces are going to go as mv squared over r, except this time we're using u, right, instead of v. We can write this then as m mass of the Earth times g times mass of the satellite over total radius squared has to equal m times u squared over r. Little m's on both sides cancel. We get that u is equal to mg over r, which again, mass of the Earth, universal gravitational constant, and then radius of the Earth plus height above the Earth, right? And if we do that, we get that u is somewhere on the order of about 7.82 times 10 to the 3 meters per second. It'll help us later. I'm also going to write this in terms of fractional speed of light. It's about 2.61 times 10 to the minus 5 times c, speed of light. And so let's start with the case where it's directly overhead. Well, we're going to use, where did I put this? We're going to use the version of the equation where f equals f naught times the square root of 1 minus u squared over c squared divided by 1 minus u over c cosine of theta. If it's directly overhead, notice that theta is going to go to 90 degrees, right? And so this is going to look like, at least for part A, I regret my not being more efficient with my board work, that f equals f naught 1 minus u squared over c squared over 1 minus u over c cosine theta. But if cosine theta goes to 90, sorry, if theta goes to 90, cosine of theta goes to 0. And so this just becomes, at least in part A, f naught times 1 minus u squared over c squared. And in this case, since u over c is going to look like 2.61 times 10 to the minus 5, well, u squared over c squared is going to be on the order of 10 to the minus 10, right? And so in this case, f really does wind up looking like f naught, because 1 minus something on the order of 10 to the minus 10 is basically 1. Square root of basically 1 is still 1. 1 times f naught. So f is basically f naught. It winds up being still our 122.450 megahertz, which is perhaps comforting. But now let's look at what happens when we go off angle. So in B, we're at a longitude 10 degrees west of the ship. So we're going to let B go to 10 degrees. Well, now the question is, how do we determine theta in that case? Well, what I see here is I can make a triangle like so. And I can now use the law of sines. I can say that if I call this angle alpha, sine of alpha over this opposite length, which is the radius of the Earth. So sine alpha over RE has to be sine of 180 degrees, right? So the total, the total triangle 180 degrees. Minus, sorry, I had someone pop by my door. I paused recording. Hopefully this picks up where I left off. We had sine of alpha over, right? Sine of alpha over this side length needs to be this angle, sine of this angle over this side length. So total angle is 180 degrees in the triangle, interior angle minus alpha minus b is just this angle, right? Over the opposite side is going to be h plus re. Yay? And so we can treating phi as 10 degrees, we can solve for alpha. Alpha winds up being about 77.3 degrees. And then if alpha is 77.3 degrees, between you and this side length, right, that should be total 90 degrees. But if we've just spent 77.3 of them here, then theta needs to be about, let's see, 12.7, is that right? 78, 80, 90, yeah. So if we then plug that back into this original equation, using our u over c of 2.61 times 10 minus 5, we get that f is going to equal, let's see, about 122.453 megahertz, while the satellite is still approaching the ship, at least partly. Now let's do the same for when the satellite is over here and it's moving away from the ship. Well, the angle winds up being the same in magnitude. And so in this case, the difference is that it's receding. And so for part C, we can just say that f is equal to f naught times, well, again, just turn u's into minus u's. Note that nothing happens in the numerator because u squared and minus u squared look the same. But in the denominator, since it was 1 minus u over c cosine theta, well, u turns into minus u. This becomes 1 plus u over c times cosine theta. And so, again, plugging in theta is about 12.7 degrees, and the u over c looks like 2.61 times 10 to the minus 5. Then this gives us that the f for part C winds up being roughly 122.447 megahertz. Note that the difference isn't big, right, over that 20-degree total span, but it is different. And note that as the satellite's approaching, it's a little higher than the satellite says it's emitting, the received value at the ship. And when the satellite is moving away, the received value is a little bit smaller than the satellite says it's emitting. Does that work? Hopefully that's not terrible. Let's try one more. So printed this out, MS Paint, my paint skills. Let's take a laser pointer. These hashed walls I intended to be mirrors, and this is just like a regular wall. Stick a laser pointer through that wall, travels down, bounces off the mirror. At least qualitatively, you know what to expect. It's going to do something like this, and it's going to bounce off this mirror, and then it's going to strike the wall here. What I want to know is, what is this length where it strikes the wall? And here we can use our law of reflection from yesterday. So our law of reflection gives us that the instant angle, theta instant, needs to equal theta reflected. And so here, note that I see a triangle. Badly drawn as it is. And it has side length 8 meters minus 3 meters, 5 meters. And length 15 meters. We could look for theta I. So we could say that, we could say that tangent of theta I is 5 meters over 15 meters is 1/3. So you go to the calculator. That is an angle of give or take 18.435. Oh, that's not fair. Theta I, this is roughly 1/3, right? But that tells us that theta I is roughly 18.435 degrees. So oh, that's not terrible. But that means if our law of reflection holds, then theta I is also theta R. And so now we have another triangle, right? Where this is also 18.435 degrees. This time, if the side length is 3 meters, we want to know what this height is. Let's call this delta y1. And so we could say that if this is 18.435, so is this, right? That tangent of 18.435 degrees is equal to the opposite 3 meters over the adjacent delta y1, or delta y1 is 3 meters over tan of 18.435 is give or take, return to the calculator, I don't know why I needed a calculator because we just inverse tangent this, but oh well, it's done now. Implies that that delta y1 should be 9 meters. That means that we have, so if this is 18.435 degrees, then, well, this angle and this angle have to be the same, right? Not 18.435, but they have to be the same. It's actually 90 minus 18.435. But that also means that this angle has to be 18.435 degrees also, right? And if delta y1 is 9 meters and this total length is 15 meters, that tells me that this has to be 6 meters. So if we want to find L, well, again, we can say that tangent of 18.435 degrees is equal to L over 6 meters, or that L is going to wind up being, is this going to be 2? Lo and behold, L is about 2 meters. Yay. Questions, comments, concerns? So I am going to pause this here. If you have questions, let me know, but we'll do more problems in lecture and we'll do more problems again next week. As always, you guys are awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your days, but not so much that we don't see you next time.